Here in this video, we're going to look at antiderivatives and indefinite integration. And if you think of the term antiderivative, we've talked about derivatives before, so the antiderivative is going to undo the derivative. So, for example, if I said I want you to find a function f whose derivative is f of x equals 3x squared. So f of x equals 3x squared is the derivative, and I want to know what was the original function f of x. So if you kind of think working backwards, what do you think the original function f of x would have been before we take the derivative to get 3x squared? Well, we know that we normally decrease our exponent. Okay, so it looks like instead of x squared, then the original function must have been x cubed. And what do we normally do with the exponent 3? The exponent, we multiply that out front, so that's where the 3 here is coming from. So how would we cancel that out? Well, instead of multiplying, we could divide. And that's certainly what we would do. So f of x equals x cubed would be an antiderivative of 3x squared. And simply what that means, if we take and we find f prime of x, then this would certainly be 3x squared. And that's what we're going to be looking at for the next couple units here, is looking at how we can use these antiderivatives. So the definition here is a function f is an antiderivative, and notice here the key word is an antiderivative. It doesn't say it is the antiderivative. A function f is an antiderivative of f on an interval I, so this is just the interval from, say, a to b, if f prime of x is equal to f of x. And notice here this is big or capital F prime of x equals lowercase f of x for all x in the interval I. And as far as the notation, you're going to notice that when we're indicating the antiderivative, we're going to be using this uppercase, or what I call big F of x. And let's look at this again closely. This says this is an antiderivative. If we go back to the problem above, and I'm just going to call this f sub 1, we said the antiderivative was x cubed, because if we take the derivative, we would get 3x squared. Now, if I gave you another function, f sub 2 of x, and what if I said the antiderivative was x cubed plus 8? Well, what do you get if you take the derivative here? Well, the derivative of x cubed is 3x squared, and then the derivative of 8 is 0. So if you notice, x cubed plus 8, here we still end up with the same function, 3x squared. And I could even go a step further and say, well, maybe the antiderivative is x cubed minus 500. Well, once again, if you take the derivative, you're going to get 3x squared, and that's going to match the function up here at the top, 3x squared. So all of these are antiderivatives of our function f of x equals 3x squared. So what we're going to have to do to take account for this, why do all three of these work plus there's infinite more? Because we have a constant term here, plus 8 or minus 500, or here we would have plus 0. We know that when we take the derivative of a constant, it turns out to be 0. So our antiderivative, we could write this as f of x is equal to x cubed plus c, where c is a constant. So that would take care of any value that we would either add or subtract to this function. So, and the reason this is any constant is because, once again, the derivative is 0. Okay, so all of these, and there's infinite more possibilities. So the way that we would write our antiderivative, the notation would be f of x equals x cubed plus c. And it's important to include the plus c because that tells us that there could be some constant added on. All right, that leads us to the definition here of a differential equation. So now we're talking about an equation in terms of x and y that involves the variable x, the variable y, and derivatives of y. So if we look at a very basic example, we have y prime equals 2, and the direction says we want to find the general solution of the differential equation. So here's our differential equation, y prime equals 2, and if we're going to solve this for the general solution, that simply means we want to solve for y. Well, if we integrate y prime, then that's just going to be simply y. And now if we integrate to this antiderivative, well, it looks like we need what? A variable x, because we know if we go backwards, if we take the derivative of y, that would be y prime. The derivative of 2x would simply be 2. So we end up with y equals 2x. But up here it says we want to find this general solution, so that means y equals 2x. What do we need to add on? Well, from up above we said that we have to add on a constant. So here is your general solution, y equals 2x plus c. Now that means that c could take on any value because it says we're looking for a general solution. And over here at the right, I have given you 3 graphs of y equals 2x where we looked at 3 different c values. And the first one here is when c is equal to 5. And the second one here, it goes through the origin, so this is where c is equal to 0. And the last one, we have c is equal to a negative 3. So here you end up with a family of functions, y equals 2x, or we think of this as a family of curves because there's many graphs that we could have here to represent this value for y equals 2x plus c, because c could take on many values. So your general solution here for this differential equation is basically a family of graphs, a family of curves here, or a family of different types of functions where you're adding on or subtracting some value of c. Now when you hear the word here antiderivative, or a lot of times you'll hear indefinite integration, they mean the same thing. We're looking at the inverse, we're going to say, of your derivative. And if we look at some notation here, this symbol here looks like a stretched out S. This is your integral sign. And this part here, the f of x, that is called the integrand. And that is the part that we're going to be integrating. That's the part that we want to find the antiderivative of. And the last part here, the dx, this is your variable of integration. And if you recall, when we were looking at taking derivatives, we would always say that when we took the derivative, we would have something like dy dx, which said we were taking the derivative of y with respect to the variable x. Well, that's kind of the same thing here with our integration. This dx is telling us that when we integrate, we're integrating with respect to the variable x. So there's kind of the 3 parts of your integral notation. We have the integral sign, the inside part, which is the integrand, and then the dx. Now, one thing I really want to stress is once you integrate, this integral sign and the dx will disappear. Okay, that's the symbol or the notation that tells you that we're trying to find this integral or this antiderivative. So once you do that, the integral sign and the dx will disappear. It's kind of like when you add two numbers together, like 2 plus 3. Once you add the numbers together, the addition sign disappears. All right, here it tells us that integration is the inverse of differentiation. So that simply means that if you integrate f prime of x dx, well, you're going to end up with f of x plus c. Because, for example, if we take the derivative of f and then if we integrate, we're back to the original function f of x. And of course, we have to add on plus c for that constant term. And what that means is if we take the derivative of this right-hand side, we would get f prime of x, which equals the inside part, the integrand. And over here, vice versa, the differentiation is the inverse of integration. So that means if we take the derivative of the integral of f of x dx, basically the derivative and the integral cancel out and you're left with f of x. So you could look at this, if you integrate this little f of x, then once you integrate you would get big f of x, and then if we come along and take the derivative of big F, then we're going to end up with the derivative, which would be little f of x. So once again, this is just showing you to verify that you realize that integration and differentiation are inverses of each other. It's kind of like if you multiply and divide. If you take and multiply some number by 2 and then you divide by 2, you're doing the inverse and they're going to cancel each other out. Okay, so at this point, hopefully you have a basic understanding of the antiderivative, where that is doing the opposite process of finding the derivative of a function. So here we're kind of undoing that operation. So the indefinite integration or this antiderivative is undoing the derivatives that we had looked at before. So we're kind of going in the reverse process. And you will look at some other videos shortly that will look at some more examples of finding indefinite integrals.